in this example, we have a double bond. And when you see a double bond, you really want to think about that as kind of a lock in the molecule. Meaning, let's just say we have this simple compound here. Even though these two hydrogen are on the same carbon, those are chemically distinct. Why? They're in different environments. One is locked opposite the chlorine, or trans to the chlorine. The other is locked by that double bond cis to the chlorine, or on the same side. So those are distinct hydrogens. So just in this simple molecule, we would have A, B, C, 3 types of hydrogens. All right, so let's come up to our example here. And if we want to do the number of distinct hydrogens, again, it might be helpful to draw in our hydrogens. And in this case, I'm actually just going to write them in on this structure. Here at the end, we have this CH3. This is a CH2, CH2, and then we have a couple of CH3s at these bond terminus. Now, as we go through to figure out our distinct hydrogen, the CH3 group on the left, that's one type. Then we have the alkene CH, that's a second type. Now we have the other alkene CH, that's a different type. And again, it's in a different environment. This one is on the carbon with the CH3. This one is on a carbon with a CH2 attached. There are 2 totally different types. Next, we have the CH2 in the chain. That'll be D. We have the next CH2 in the chain. That'll be E. One's closer to the double bond, one's further away. That makes them distinct. Then we have a carbon with no hydrogen, so nothing to worry about there. Then we have the methyl group, which will make F. But this methyl group is on this carbon. This methyl group is on the same carbon. There's free rotation around the single bond here. So depending on where these are at any given time and space, you can't distinguish them. So both of those methyls are equivalent. So these 3 hydrogen are equivalent to these 3 hydrogen. They're both F. And then the hydrogen on the OH is G. Even though it's not on a carbon, it's still a distinct type of hydrogen. This molecule then has 7 distinct types of hydrogen. Now let's count the carbons. Just to give us a clean structure to work with, I've redrawn it. All right, don't forget, every time you have a termination point, that is a carbon you have to account. So here we'll say that CH3 is carbon A. Then we have the 2 carbons of the double bond. One is B, one is C. They are distinct. B has a methyl group attached. C has a CH2 group attached. Different environments. Next we have the CH2D, the CH2 carbon E. Then we have this carbon here that we ignored before because it didn't have any hydrogen. But if you're figuring out the distinct types of carbon, that is a distinct carbon type. So that will be F. And then the 2 methyl groups are still equivalent. Those will each be G. So this molecule has 7 distinct types of carbon.